Hello, I'll be presenting Lab 1 from Physics 1, and this is the constant velocity lab, and I will look at the movement and velocity of a golf ball. So, like I said, this lab we are looking at the constant velocity of an object, and we're exploring how Newton's second law relates to force and velocity, and how the position function relates to the velocity and time. The assumption for this is that the net forces acting on the system are zero, and we also used computational modeling in order to predict what a computer would say the position would be of an object that did have this net force of zero. And this is very important in physics nowadays because computers are everywhere and we're able to actually do these models without needing to actually be in a lab. We could look at it on the computer, which is what we did in this lab, which is extremely beneficial. So the objective was to pick an object moving in the same direction at the same speed and analyze it by understanding and predicting its motion. I decided to pick a golf ball rolling across my kitchen table and using Newton's second law, predict the motion. The model of this experiment, like I said, is working under the assumption that the net forces acting on the system are zero. And this picture shows what I did in Tracker when I observed the golf ball, and I calculated the values of the observed data from this. So here is the graph that I found from Tracker, and as you can see, it's not a perfectly straight line. It's got a couple dips here and there, and that's because it's observed data, so it's not a perfect system. But this is the data that I extrapolated in order to find the constant velocity. And so the start time was 0 seconds, and the initial position was 0, 0, and 0. And at time 0.033 seconds, the ball's position was 0.0106 in the positive x direction, and then 0 and 0 meters. And in order to find the velocity, this is obviously the equation. It's going to be your change in position divided by your change in time, which is exactly what I did with those vectors there. I did the final position, which really was just the second position because you could use really any point in order to solve this equation. And so I used the second point. And so ended up getting 0.32 in the positive x direction, 0 and 0 meters per second. And we're just looking at the position in the x direction here, and that's obviously what I got. And it's very interesting to be able to actually take an object in real life and track its velocity like this, which I thought was a very beneficial part of the lab. And the time of my last observation was that 0.6 seconds. And in the next slide, you will see the difference in the coding model that we came up with in comparison to this one. And then using GlowScript, I decided I was going to plot those points, and this was using the coding that we were given, and I mimicked it to my data. So time obviously less than 0.6 seconds. I inputted my velocity and inputted my delta t, so that's a step in time, and this is the graph that it shows. And it more or less mimics the graph that you saw on the last page, which was found directly using Tracker. But it's a more perfect line. It's more perfect y equals x. And so I'm going to discuss why there's that difference there in the next slide. So like I was saying, this is the computational data versus my observed data. So that's the GlowScript data versus the data that I actually saw within Tracker. The light blue lines, the observed, and the dark blue lines, the computational. And obviously these aren't exactly the same. And if my system that I was looking at on my kitchen table with my golf ball, it should mimic the computational data if it was a perfect system. However, I concluded by looking at these two lines that there must have been forces acting on the object so that it did not have perfect constant velocity. So those forces could have been friction, it could have been maybe my kitchen table was slick, could have been my kitchen table was rough, so the friction there, or the fact that the force that my hand projected onto the object was not kept over that same period that we were looking at. So in conclusion, asking what if the orientation was not set in the positive x direction that I had it in, would you still be able to get those same results and find that constant velocity? And the answer is yes. It would change the data. Obviously, they would be different numbers, but the relationship between position and velocity would be the same. And also, there were definitely pushes and pulls acting on the object. However, you hypothetically should be able to get a net force of 0. So there's the push of my hand on the ball, and then there's the push back of friction in the other direction, and then there's the pull of gravity, and then the force of the table back on the object. So these technically should be able to equal 0. However, as you saw in my last graph, they did not, because it was not a perfect system. But overall, this lab was a great representation of how we can see Newton's laws acting in real life.